The first data structure of many that we're going to talk about that is sequential based is something called a linked list. Okay? So we said that in Java there is something called a list, and then an array list behaves like a list. Okay? So a linked list also behaves like a list in that they support the same operations like adding an element, setting an element, removing an element, let's see, what else? Add, set, remove, retrieving an element, and things to that effect. The thing is, they each do them differently. Okay? So, remember that we said an array list, for about the 40th time now, it will resize its underlying array when the capacity is exceeded. Okay? So you get something that maybe looks like this with, more slots in the underlying array. So the difference, however, is that linked lists don't do this at all. They're not represented by an underlying array. So instead, an array list looks something like, a linked list looks something like this. If we have an element, let's say that it looks like this. Elements have two things to them, at least in a general implementation of a linked list. They have something called the data and then something called a next pointer. So what do I mean by that? I mean that, let's say we have a linked list of numbers, and we can create one by just doing list of integer L equals new linked list rather than array list, and that will give us a linked list. Okay, so what do I mean by this? I mean that let's say we have a node, which is what these are called, an element with the value 120. What's going to happen is this box, this thing, is somewhere located in memory. Let's say it's located at address 0xab. Okay? What's going to happen is when we add a new element, we're going to create a new box with some value. So let's say we have the operations l.add, and let's do 120, the first thing we added. And let's say we add the value 42. Okay? So what's going to happen is we're going to create a second box with the value 42, and then this first element is going to point to the second element in the linked list. Okay? And now the important thing here is that these two boxes are not necessarily contiguous in memory. This one might be at address C123, for example. So it can be really, really far away from this box in memory. Okay, let's add another element. So let's say we want to add the value 18. Okay, so again, we're going to create another box with the value 18. And then now this box is going to point towards this one, or point to it, not towards it. And again, this can be at, let's say, at address 0xff. So the thing is, we don't know where in memory these things are going to be located, and whether they'll be in proximity to one another. So let's say that this is a 3-element list. So the last element is then going to point to null, because there's nothing there. Okay? So while an array list is a data structure that uses an array as its underlying implementation, a linked list uses links, as the name implies, and nodes to describe its elements. Okay? So each of these things is a node. And like I said, they have a value, which is the data. They have a next pointer, and a location in memory, or rather, they exist at a location in memory. Now, we said that if we are going to, let me think about how I want to phrase this. So, remember that we said array lists have this thing called constant lookup time. Sorry about that. They have this thing called constant lookup time. And remember that we said that all this means is that the if we know the index that we're looking for, I, we can just immediately find it by doing .get, and that's just an offset from the first element, because, again, an array list is just an array. And if we know this box, if we know the address of this box, then we know the address of this one. Well, we know the addresses of all of them, right? Because it's just a multiplicative offset. So that's why we get this constant lookup time. Unfortunately, linked lists don't have that luxury, so we don't know where an element is in memory. So we don't get this constant lookup time. So if we have an index I, then the only way to find it or to get its value is to just follow these links. So if we're trying to get the value at index 2, we're going to start from what's called the head of the list. Or actually, let me think. So let's use this terminology. So we have the first thing in the list, which is this thing. Then we're going to follow its links. So we're going to go from 0. So this would be at index 0. This would be at index 1. Then this would be at index 2. Okay? So the only way you can get from one element to the next is to follow these links through either recursion or through a loop. Okay? So that's one of the big downsides of linked lists. Okay? But one of the good things about them is that you can insert elements and you can remove elements in what's called linear time. And all that means is that if we know that we want to, let's say we want to insert the value, let's say we want to do l.add 2 and then 200. Okay? So in order to get to this index, we have to go to the spot where it could be. So what we're going to do is we're going to go from 0 to 1, and then we're going to create a new box that says, what? That says 200, right? So this is going to be the new index 2. And then what we're going to do is just change what the previous thing is pointing to. So now this element points to this node, and then this one points to this one. So no chains are broken. Okay? So this one goes from index 2 to index 3. Okay? Let's say we want to do the reverse of that. Okay? So when I say the reverse, I mean the opposite rather. I just mean that we want to remove an element instead of adding one. So let's say we want to remove the value at index 0. Or sorry, let's do 1. I think that's a little bit easier to illustrate. So if we want to remove the value at index 1, or the element at index 1, we can just go to that element, that index, and then we can just simply change what this is pointing to, and just say that it points to the thing that the next element is pointing to. So we're just changing what things point to. Now, what will happen is that this element will get garbage collected. So remember that this thing, or in order for something to get garbage collected, it has to be unreachable. Okay, we talked about that with relation to arrays. Okay, this element is now unreachable because nothing references it. It doesn't matter if it references something else, it's that nothing can directly get to it, so Java will just reclaim this thing from memory. Okay, now these two indices will change. This one will become index 1, this one will become index 2. Okay, and hopefully you can see that this is much faster than just inserting an element at the front and having to shift everything over, or having to insert anything and have to shift anything over. Okay, that's the big issue with insertions and removals from an array list. And we have a small code example here to illustrate that. So what I've done here is we created a linked list, and what we're going to do is we're going to add 1 million elements to this linked list, and we're going to do it from the front. So we're just going to add a bunch of elements to the front of a linked list. Okay? So we're going to have a print statement that just executes when the loop is finished. Then we're going to do the same thing for an array list, and we're going to see how long this takes. So let's see. Let's run it and let's see. Okay, first one's already done. That was very quick. And hopefully you can already see that doing this with an array list is very slow, because we're going to have to shift everything each and every time. Okay, so the more elements we add, the slower it's actually going to run. Okay, so again, still sitting here. I don't think we should sit here for much longer because it will probably take a while. But let's go back to the let's go back to here, and then we'll finish off. So that's the nice thing about a linked list, that we can just insert and remove elements arbitrarily and it be very fast. Okay, but of course linked lists are not the solution to everything, and there are two other sequential data structures that we'll talk about that allow us to essentially get some of the things that a linked list does, but in a more primitive fashion. Okay, so the reason why I'm saying it that way is because there are these two data structures called stacks and queues, and they are actually you can get the functionality of a stack and a queue from a linked list, but we should definitely at least talk about stacks and queues because of their historical significance.